Welcome to the session on lattices and codes. The first talk is about rigorous foundations for dual attacks in coding theory, and it will be given by Charles Meyer Hilfiger.
Hello. Okay, good. Thank you. So I'm going to present you joint work with Jean-Pierre Tillich about dual attacks and their analysis. So dual attacks solves the decoding problem in code and lattices, and this problem is at the heart of security of all code and lattices-based cryptographic primitives. For example, dual attack would impact Kyber parameter, which is an NIST standard. The problem now is that independence assumptions are made to analyze the complexity. And it turns out that they are not valid. In codes, for example, Carrier and al. showed noticed experimental differences between what we should obtain under this independence assumption and what we obtain in real life. And in lattices, Duca and Poole showed that these independence assumptions just could not hold in certain regime. And this seriously questioned dual attacks. So the question really is now, does dual attack really work? And so the contribution of our paper is to show that dual attack in coding theory work. And to do that, we give rigorous foundation for analyzing them without using any independence assumption whatsoever. So first of all, I'm going to talk about dual attack and their analysis. So I said to you that dual attack solves the decoding problem. So what is the decoding problem? It's just that I will give you a binary linear code, which is just a linear subspace of F2 to the n. And what I give you also a noisy code word of this code. So I give you a y here, which is equal to a code word plus an error vector, which will be of small Hamming weight. And I ask you to return me this error vector. So the main ingredients for dual attacks to solve this problem will be to use the dual of the code, which is just the elements of the ambient space, which are orthogonal to all of the code word of C. So the thing is, when I say orthogonal, it's for the usual inner product in F2 to the n. And here the element of the dual code, H, will be called parity checks. So the main idea of dual attacks is just to notice that if I take a parity check, which is of small Hamming weight, then I can compute y dot product h. Y is my noisy vector. And this is equal, by definition of y, to c dot product h plus e dot product h. And so, no. Okay, thank you. So what did I do wrong? This. Okay, no, good. Okay. So, so what you have, it's that here, because C is a code word and H is a dual code word, this term cancels out and you only have left E dot product H. And because E is an error vector of small Hamming weight and H is of a parity check of small Hamming weight, this dot product will be biased towards 0. So it will be equal to 0 more often than it is equal to 1. And so the whole idea behind this is you can make use of that, for example, of that principle to make a distinguisher, for example. So let's put aside the decoding problem for now, and we can build, using this, a distinguisher between a random y and a y which is a noisy code word. And what you will do is actually you will compute the bias of this quantity, and you will say, okay, if the bias is high enough, this is mostly, with high probability, a noisy code word. So more formally, what I do is I compute all the parity checks of yw, and then I will compute this bias function, bias of y, and essentially it's a sum over the parity checks of yw of some terms that is between either -1 or 1. And I normalize this sum so that everything lies between -1 and 1. And so, for example, you see here that here y dot product h, if y is a noisy code word, this will be equal to 0 often. And so this will be equal to 1 often. And so this term will be big. So the sum will be big and will be close to 1. So you make a decision. If the bias is big enough, you decide that y is noisy code word. The thing is, how big is big? So when you have a noisy code word, in fact, you have a theorem from Carrier and al. That states that the bias related to y is in fact just a function of w, the weight of the parity checks you computed, and the weight of the error. Okay? And so here, you can see that essentially this function, the bias, decreases exponentially fast in the weight of the error. Okay. So now I'm ready to give the most recent dual attack, which was introduced by Carrier and Al. The idea here is really to solve the decoding problem. So to recover part of the error, at least. So what we do is we split the support in two complementary parts, completely arbitrary, P and N, and we will try to recover the error on the part P. And what splitting the support in two parts, what it really does is that it actually enables you to have quantity that will be much more biased towards zero than the previous quantities. So for what we do, in fact, we compute parity checks of weight W, but are W small on just the part N. And we do as before, we compute Y dot product H. This is equal to E dot product H as before. And now we split this dot product between the part on P and the part on N. Okay. And now by reordering this equation here, you see that Y dot product H plus EP dot product HP is equal to this quantity here. And because E on N is an error vector, actually, so it's of small Hamming weight, and Hn is constructed of small Hamming weight N here, this quantity will be biased towards zero. And the thing to notice, of course, is that because the support is smaller and because we will be able to take W much smaller than previously, this is very, very much biased towards zero. So it's a good thing for us. And so what is our algorithm? Basically, is that we will make an exhaustive search. We will compute for every X the bias of this quantity, and we will just return the X such that this quantity is the most biased towards zero. And we will hope that this maximum is given by EP. So more formally, what we do is, as before, we compute the set of all parity checks of weight W on N this time, and we compute a bias function for every X. So this is, as before, a sum. And of -1 to the power of Y dot product H plus X dot product HP. And you notice, of course, as before, that if X is equal to EP, this will be equal to 0 often. And so this whole sum will be big and will be close to 1. So you will return X such that the maximum is given by, so the maximum, so X such that the bias is maximum. So now the question is, okay, how do you analyze this kind of dual attack? You just have to study the probability that the bias related to EP is superior to the bias related to all of the other X's. So Carrier and Al gave a precise estimate of the bias related to EP. They showed that under certain conditions, it could be expressed as a function of W, the weight of the parity checks, and the weight of the error term. Okay, so this is good and this is well approximated. And now to study the bias of all the other X's, it is now that we need to make independence assumption because it's not so clear when X is not equal to P what this bias is. And essentially we make independence assumption, and this will allow us to say that the bias related to X is in fact a centered normal with a variance that we can compute. So this is in fact very, very convenient for us because then we can study this probability quite easily. So, okay, so we have this independence assumption that gives us this model. So I sum this in a plot. Here in green, you have under the independence assumption, the supposed distribution of the bias of X. Okay, so all the X that are different than EP, for example, here you see that you don't expect any X's different than EP to have a bias which will be superior to 0.05. Yeah. So for example, if you choose your parameters so that the bias related to EP is superior to the threshold, for sure you will know that, okay, with good probability, the maximum will be given by EP. So everything is good. The problem now is that you can run experiments. And so this is an extremely pathological case. So you have to, but the thing is, you see that experimentally, when you plot the distribution of the bias, for some parameters, it's not at all, it does not follow the green curve here. And in fact, what the problem is that the bias related to EP will be completely lost among many other X's, so you won't be able to recover it. So the first goal of our paper was in fact to understand this red experimental curve, to be able to make to understand it, to be able to make an analysis after that. Okay, So so the contribution is, one of the contribution is to give a distribution of the bias that will match the experimental curve. So what we do is, in fact, first we give a dual expression for the bias related to X. So I recall to you that X was defined as a sum over some parity checks. And when I say here we give a dual expression for X, it means that we will express it as a sum over code words. And essentially, we can show that this bias here is a sum over the product of two terms, Ni in this term here. And essentially, this term here to the right will be, you recognize it as before, it will be decreasing exponentially fast in I. And Ni is just the number of words in a certain code, which are a distance I of my error vector En. And this certain code, Cx here, is just the code which are such that it's just the code word of C, which are such that C on P is equal to X plus EP, and we are just only considering the distance and the N part. So actually, yeah. And so the thing is now you have these two terms that will be competing, because Ni, when I increases, will be increases exponentially fast, and this will be decreasing exponentially fast, this term on the right. And the problem now is that, in fact, you know, I said we want to study the distribution of the bias. The thing is, the only random term here is Ni. And the problem is we don't know much things about this distribution. We only know the expected value and the variance and some other things, but okay, so we don't know a lot of things. So to have to model the distribution for the bias, we need to give a model for this Ni. And it's what we did. We said that essentially the Ni were Poisson variable with good expected value, and the expected value, we can compute it. Okay, and so of course this model doesn't come from nowhere. It was very rational. And now what we do is with this model, we are able to predict perfectly the distribution of the bias, which is the distribution of the bias. So you see here that the red curve is this curve here, and the blue curves is represent the bias when we replace the Ni by the Ni by the Poisson model, as I said. And so it matched perfectly with the experimental model. So now we have all the tools to, in fact, so now that we have a model, we can study the probabilities that, we can study the distribution of the bias and study the probabilities that EP gives the maximum bias. So, so this model can be used to analyze dual attacks. And in fact, we showed in our article that the most recent dual attack introduced by Carrier and al. Just need a little algorithmic tweak to be able to achieve the originally claimed complexities. And so what does this really shows is that dual attack encoding theory work. And in fact, lastly, you saw, so the whole point of the article, not the whole point, but key point of the article was to use this duality formula to be able to give another model for the bias. And this duality formula could, in fact, be also used to analyze the dual attack in lattices. Thank you very much.
Thank you. Any? Hi.
So does it change the security levels that we need for lattice-based crypto systems?
In fact, I don't think when this attack, the Carrier and al. Attack, beats a lot of previously beat the previous best algorithm to decode random linear code, but only in certain regime of parameter. And it turns out that the regime it attacked was not used by it's not used by any how do you say by any scheme. For example, here when we did our analysis of Carrier and al., we studied the complexity of the algorithm at the Gilbert-Varchamov bound, and so it's basically it's at the hardest point, and so it's only used in signature. So okay, but the problem is usually they take rates that are 1/2, and our algorithm beats all the previous algorithm for rates that are smaller. In fact, so.
Does it the new estimates incorporated into the lattice estimator that everybody used to assess security levels?
Sorry, can you repeat?
The lattice estimator, the Martin Albert estimator, do these things already incorporated in it?
So you mean the new analysis?
Yes.
No, because actually for now, there is no, so the state of the art now is just that Duca and Poole said that there was a problem, and so there is nothing which is out yet which solves this problem. So first, yeah, the first step would be to understand the BDD scores and then to say, okay, is there a problem? But actually, we had to change the attack by Carrier and Hall a bit to be able to, the attack, we had to change it. So I don't know if it was your question, but okay.
Listing the speaker again, in the interest of time, can take questions offline.
Oh, pardon.
The next talk is on ideal SVP, hardness of ideal SVP, and the speaker is Benjamin Wesolowski.
Thank you. So this is a joint work with PhD student Joël Felderhoff, Alice Pellemari, and Damien Stellet. And I'm going to be talking about ideal SVP and how it's hard for small norm uniform prime ideals. So first, a few words on ideal SVP. What is it? I'm not going to be very long on reminding you what a lattice is, but still I want to define ideal SVP, and in particular the SVP part in it. Pointer is a bit wonky. Okay, so a lattice is described by a basis in a vector space, V1 up to Vn, and the lattice generated by this basis would be all the integer linear combinations of these basis elements. So here's an example. You have a basis, and all the points in the background are the lattice points. Now, SVP just asks you to find the shortest vector in this lattice, or the point that is closest to the origin other than the origin, or maybe not the shortest, but up to some approximation factor. So that's for the SVP part. Now, what's ideal about it? It's just that some lattices have something extra, some additional structure, which we call, which makes them ideals. So for example, look at polynomials with rational coefficients, Q adjoint X. That's a ring. And if you quotient it by the polynomial X to the N plus 1, for some N's, when N is a power of 2, say, that is going to be a field. So it's a field, which is also a Q vector space of dimension N. And in that vector space, you have lattices. One very special lattice is the one that you obtain if you look at polynomials with integer coefficients. Z adjoint X, quotiented by the very same polynomial. It is discrete, and it is in this vector space. It is a lattice in there. It's also a subring, because if you take two polynomials with integer coefficients, you get, and you multiply them, you obtain still a polynomial with integer coefficients. Now, this is a very particular example of an ideal lattice. More generally, an ideal lattice in K would be any lattice in K that is stable under multiplication by O. So a lattice A in K such that O times A is still in A. So you have different kinds of ideal lattices in there. An important family are the integral lattices, and these would be the sublattices of O that are also ideals. Now, among these integral lattices, you still have even more special ones, which are the prime ideals. And prime ideals are integral ideals that do not factor as products of other integral ideals, just like prime numbers. And they are really the building blocks for ideal lattices, integral or not. Any ideal lattice can be written as a product of prime ideals to certain powers. And when the powers are all positive, you get an integral ideal. And when some are negative, you get a non-integral ideal or a fractional ideal. So ideal SVP is just SVP in these special lattices. Why do you care? Why do we care about them? Ideal lattices have played and still play today an important role in lattice-based cryptography. They led to the first fully homomorphic encryption scheme by Gentry in 2009. And today they are still relevant in the analysis of practical crypto systems. They are the simplest case of what we call modular lattices that are used in the real world. Think Hyper and dilithium. And so they are important, but they're also very special. And this should raise some concern. Is SVP still hard in ideal lattices? Because now you've added all this extra structure and you may be concerned about making the problem simpler. And indeed, there are specific algorithms for SVP in ideal lattices that don't work generically. Still, ideal SVP is considered hard because even though we have better algorithms, they don't completely solve the problem. All they can do is reach slightly better approximation factors than we can do in generate lattices. So here we're interested in the hardness of ideal SVP. And more specifically, what's interesting for us for applications in cryptography is its average case hardness. So the question we ask is ideal SVP hard on average? And what we're aiming for is really some random self-reducibility. We'd like to prove that if we can solve ideal SVP for random instances, then you can solve ideal SVP in the worst case. And of course, for that question to be well-defined, you need to state what it means to be an average or a random ideal. And for that, you need to specify a distribution. And really, there isn't one single good answer for that. And indeed, in the literature, we've seen several distributions considered. And for two of them, we already have random self-reducibility results. The first one was precisely used by Gentry. And he proved random self-reducibility for the following distribution. You look at the collection of all prime ideals. That's infinite. But now you put a bound on how large they're allowed to be, or how big their volume can be, or more precisely than their norm. And now that's finite. So you can pick a uniformly random one. You pick a uniformly random prime ideal. Now you invert it. And this inverse of a prime is the ideal that Gentry is looking at. So he proves random self-reducibility for that, but maybe that's not fully satisfactory. What you get is not an integral ideal. Maybe it doesn't feel so natural. Why did you have to take this inverse? So that's what works for Gentry's purpose. The reason being that he's not actually looking at SVP, he's looking at BDD, and the two problems are kind of dual to each other. And this duality implies that he's looking at inverses when we look at SVP. So not exactly what we want. Another interesting distribution was considered by BDPW20, where it is observed that if you look at the collection of all ideal lattices, it actually itself forms a geometric space. It's something that looks like a torus, and you point on the torus would be an ideal lattice. So you naturally have a geometry on that and a measure on that, which we call the Haar measure. And you could uniformly sample ideals according to that measure, and that would give you a random distribution of ideals. But that would be a continuous distribution. Problem, you can't really compute with actual continuous things, so you need to discretize that. And once you discretize, you run into some trouble because your discretization forces you to pick ideals that have a rather large norm. So this is very nice. It's geometrically canonical. You have a very rich mathematical theory around it that allows you to prove many things about this distribution. But now you have to deal with ideals of large norm, which is not exactly ideal. I'm not going to use that. I'm going to call this the first version P inverse ideal SVP, and the second version Haar ideal SVP. And the one we want, the one we're looking at, is the following one. You just pick a uniformly random prime ideal of bounded norm, just like when Gentry did. But now that's it. You don't invert it. You just use that one. And now it's integral, unlike Gentry, and it's of small norm, unlike BDPW. And these are two good properties you want if you want to compose this with other security reductions, in particular for ntrue. So this works well with ntrue, and it implies a link between ntrue and worst case ideal SVP. I'm going to go back to that at the end of the presentation. So I'm going to call this version P ideal SVP for prime ideal SVP. Here's what we're doing. We're actually using Gentry's results. So he says worst case ideal SVP is it is no harder than P inverse ideal SVP. And now what we say is P inverse ideal SVP is itself no harder than P ideal SVP. An important caveat here is that these two reductions are polynomial time given a factoring oracle. So quantum polynomial time, classical sub-exponential time. And we don't know currently how to remove the need for this factoring oracle. So let's see how the second reduction works. We want a reduction from P inverse ideal SVP to P ideal SVP. So you're given as input the inverse of a prime, and you can assume that this prime has been sampled uniformly at random of bounded norm. What you're looking for is a small element in that ideal A, that inverse of a prime. And to help you, you assume you have an oracle that can solve that problem for primes instead of inverses of primes. But here are the main steps. First thing, you observe that you are being given the inverse of a prime and you're looking for a small element in there. In particular, you have a prime and you have an oracle that's good at dealing with primes. So maybe you can just do that. You feed your prime to your oracle and it gives you a small element in there. Of course, that's not what you're looking for because you want a small element in its inverse, not in the prime. So you're not done that yet. Second step is where everything's happening. And I'm not going to have time to detail how we do that, but here's what we're expecting it to do. We want a sample ideal algorithm that on input, an ideal and a small element in it, will return a pair by, where B is simply a uniform integral ideal of bounded norm, really just a random ideal independent of the input. And now Y is going to be a small element in BP inverse. So it sounds easy to generate uniform random ideals. It doesn't sound so easy to first generate the random ideal and then find a small element in that other ideal. And that's not how you're going to do it. Of course, think of it as some kind of trapdoor generation where you're essentially going to generate Y first and then find a B that suits it. And this is really the non-trivial part. It's where we need the factoring oracle. Third step, you're going to say, all I care about is primes. If B is not prime, I just abort. So there's a success probability here that is proportional to the density of primes. And luckily, we understand very well how dense prime ideals are among random ideals. Now you have B that is prime. And before you were sure it was prime, it was uniform among all ideals. So now it's uniform among all prime ideals. And that, again, is precisely what your ideal is good at dealing with. So you feed it to your ideal. To your oracle, sorry. And it finds a small element in B. So you find SB and B that is small. Now you found two small things, SB and Y. Take their product. SB was in B, Y was in BP inverse. So their product is in P inverse. And now why is it small? Simply because SB and Y are both small, so the product is small. And well done, we found a small element in P inverse. So these are the main steps of the reduction. The hard part, and yeah, most of the work goes into the second step and showing that you can actually do this sample. Let's go through the application to Entru. Entru was introduced in 1996, and in 2021, Pellemari and Stele gave a CARP reduction from ideal SVP to Entru, which means they give a translation. If you have an ideal SVP instance, you can turn it into an Entru instance. So that gives us a way to create Entru instances. If you have a way to generate ideals, turn them into Entru instances with their reduction. So we can do that with our distribution. Sample a uniformly random prime ideal P, feed it to this CARP reduction, you get an Entru instance. And you can do that carrying along also a trapdoor. And we call this distribution D-Entru. By construction, thanks to their CARP reduction, we have that solving Entru for that distribution is at least as hard as the P-ideal SVP problem. And now the P-ideal SVP problem we know is at least as hard as worst case ideal SVP. So we have a connection between Entru for some distribution and worst case ideal SVP. This is in fact the first distribution over Entru instances with a polynomial modulus whose hardness is supported by worst case lattice assumptions. And you could not do that with the previous reductions because the norms would be too big or the primes would not be integral. The obvious caveat here is that to do this reduction, to sample this distribution, you would need a factoring oracle, which we don't have. So open question here, can you remove the need for this factoring oracle? Thank you for your attention.
Yeah, very nice. I was wondering, have you looked at all into for sort of concrete parameters that we want to run Entru for, whether the factoring is actually something that's feasible, or because we also don't need, to generate a ton of them, right?
No, we haven't looked at what practical sizes of parameters that would be. Indeed, factoring random integers is not always hard.
Yeah.
It will depend on what integer you have. And for many of them, it's going to be easy. And if the numbers are not so big, it may always be feasible. But yeah, I have no clue what it would look like for complete parameters here.
Okay, thanks.
Okay, let's thank the speaker again. The next talk is about the multi-user security of LWE-based non-interactive key exchange by Roman Langer.
Thank you for the introduction. Let me start with a brief recap what non-interactive key exchange, or for short NIKE, is. It's a cryptographic primitive that allows any pair of users to obtain a common shared secret key using a public key infrastructure. So in more detail, we have a setup algorithm that outputs public parameters, which can be used by every user to generate its public secret key pair. And then any pair of users, so for example, Alice and Bob, then Alice can use her secret key and Bob's public key to compute the shared key, and Bob can use his secret key and Alice's public key to compute it, and they should be the same. A famous example for this is the Diffie-Hellman key exchange, but this talk will be about an instantiation from the LWE assumption. And for this, we have to slightly relax the notion of NIKE. So we ask these shared keys to be the same only with high probability. The most basic security definition for NIKE is light security. There the adversary gets the public key of two users and a real or random shared key between them. And this goal is to distinguish these two scenarios. However, this security notion only really captures scenarios where a public key is used just once, so to compute one shared key. A more realistic security notion is adaptive honest key registration, for short HKR security. And that is defined via a game in which the adversary can adaptively create new users. He can corrupt users, so that means he gets their secret key. He can reveal shared keys between any pair of users, and he can do the challenge as before, so select two users and then gets a real or random shared key. An even stronger notion is adaptive dishonest key registration, for short DKR security, where the adversary gets one additional power, and that is to introduce maliciously generated public keys. So that means he can generate public key maliciously, and then in particular ask for shared keys that are computed with, for example, a challenge user's secret key. Adaptive DKR is probably the most realistic security notion and also the strongest. It implies adaptive HKR, which implies light security. It was shown before that light security also implies adaptive HKR security for NIKEs that have a negligible correctness error. And in this work, we show that this negligible correctness error is necessary for a generic argument. It was also shown before that if you add a NISIC proof of knowledge of the secret key to every public key, you can get from adaptive HKR to adaptive DKR security. However, that works only for NIKEs with perfect correctness. And the results from this work also imply that this perfect correctness requirement is necessary here. Okay, now let me get on how you get NIKE from LWE. So the public parameters is a random square matrix. And Alice and Bob now both sample a short LWE secret. So for example, a binary distribution can be used and a noise vector, typically a discrete Gaussian. And Alice will multiply her secret from the left-hand side to this matrix A and add the noise, and that's her public key. And Bob will do the same, but multiply his secret from the right-hand side to this matrix A. And the secret key is always the LWE secret. So you notice there's a slight difference between how Alice and Bob generate their public keys. to get a full-fledged Nike where every pair of users can generate or compute their shared key, every user, in fact, has to generate an Alice type and a Bob type public key. So how do they obtain the shared key now? That works as follows. Alice computes the inner product between her secret key and Bob's public key. And for security reason, she also adds some noise to it. And Bob does the same thing. So he computes the inner product between Alice's public key and his secret key and adds some noise. And then they get the terms that are here on the slide. And if you look at the black part, that is the same. And that is a large value because the entries of A are large. But there's also this red part, which is different. However, the red part is short because both the secret and the noise is short. So these values are approximately the same. And by simply rounding these values, we can get the shared key that is the same with high probability. So if you use a polynomial modulus to noise ratio, this means you get a non-negligible correctness error. And if you use super polynomial modulus to noise ratio, you can get a negligible correctness error. And there's an impossibility result by Huo et al. That shows that this correctness error is really hard to avoid. However, I think the Nike is still useful despite this correctness error. For example, because there's a protocol that allows you to correct this correctness error with just one bit of interaction. So what about the security of this Nike? Well, the first work by Ding et al. And Picard proved only light security. We've seen before that with this generic arguments, that means for super polynomial modulus to noise ratio, we also have adaptive HKR security. And until recently, there was nothing known about the empty parts of this table. A concurrent work to this showed that a variant of this Nike that also uses the QROM model can achieve adaptive DKR security. In this work, we show that for a bounded number of users, you can get adaptive HKR security even with a polynomial modulus to noise ratio. And we also show that with the polynomial modulus to noise ratio, the Nike is not adaptive DKR secure, even if you add these NISIC proof of knowledge. And for super polynomial modulus to noise ratio, we show that if the noise you add to the shared keys is only polynomially larger than the noise you use for your public keys, it's still insecure. But if the noise is super polynomially larger, it becomes secure. Okay, now let me briefly recap how the light security proof for this Nike worked. So in the light security game, the adversary gets all these parts that are marked here in blue. And security proceeds via hybrid argument. In the first step, we switch Bob's public key to something uniformly random, which is a straightforward reduction to the LWE assumption. And in the second step, we switch Alice's public key to uniformly random. And more importantly, we also switch this value KAB to uniformly random. And this works by applying the LWE assumption to a matrix that has as top part this matrix A and as bottom part the public key of Bob. So what's the problem with getting adaptive HKR security? Well, the reduction can just guess the two challenge users. And then there's actually only one thing left to do. And that is the shared key queries where a challenge user's secret key is used. So for example, assume that Alice is again a challenge user and the adversary asks for the shared key with Charlie, but Alice's secret key should be used to compute this. So he gets this value round of KAC. Then it seems the reduction needs to know this value KAC, which can only be computed with Alice's secret key, and we have to avoid that to use the argument from before. The reduction can, of course, compute KCA, so the shared key compute with Charlie's secret key, but they are slightly different. So they differ in this red part. And our idea is to use the leakage resilient of LWE to make the reduction just know these red parts. So the first part is leakage about the secret, which can be justified, for example, by a result from Brakersky and Döttling. The other part is leakage about the error. And for this, we use a result from Döttling et al. From Eurocrypt that shows that noisy linear leakage about the arrow is okay. And this works fine here because we anyway have the noise for the shared keys. This way we can get multi-user security, but the LWE dimension n now has to grow linear with the number of users. So this is better than the trivial solution to use a public key, a new public key for every shared key, but it's not that much better. This really becomes useful with our second trick to reduce the amount of leakage. And the idea is quite simple. The adversary actually does not get this value KAC, he only gets the rounded version, round KAC. And quite often, these rounded values, round of KAC and round of KCA, are the same, and then we don't need any leakage. So if you imagine, for example, that the rounding function looks like this and rounds everything here that's on the right-hand side to the bit 0 and everything on the left-hand side to 1, then if this value KCA is quite far away from a rounding boundary, then we don't need any leakage. But when it's quite close to a rounding boundary, then we do need the leakage. And to get this into a formal argument, there's one challenge, and that is that the leakage on the secret must not depend on the matrix A. However, whether KCA is in this red zone close to a rounding boundary or not clearly does depend on A. However, we observe that the leakage we need is SA transpose times EC, and EC has only very small influence on where KCA is. And this can be turned into an argument that avoids this dependency on the matrix A. So this way we get multi-user security where the number of users can grow polynomially in N, and this polynomial depends on the modulus to noise ratio. Thank you.
Questions for the speakers? Listening the speaker again. Yes, the last talk of the session is about revocable cryptography from learning with errors, and it will be given by Prabhanjan Anna.
Okay, so I'm going to be talking about revocable crypto and how we can build it from learning with errors. This is a joint work with Alex Pramba and Vinod Venkatanathan, both from MIT. So quantum computing can be both useful and harmful to cryptography. In this talk, we'll see how it can be useful to cryptography. Specifically, we're going to focus on the area of unclonable cryptography, which is about how to leverage the no-cloning principle of quantum mechanics to build crypto primitives that are impossible to achieve classically. So roughly speaking, the no-cloning principle says that it should not be possible to clone arbitrary quantum states. And this is not a new area, and it has been there from the 80s. The very first primitive that was introduced was quantum money by Weissner. It's arguably one of the most popular primitives in unclonable cryptography. And since then, there have been many interesting unclonable primitives, including unclonable encryption, copy protection, which I'm going to briefly talk about now, certified relation, software leasing, and so on. Okay, so let me talk about what copy protection is all about. So roughly speaking, copy protection is about leveraging the no-cloning principle to achieve software antipiracy, meaning that I'm going to associate software with quantum states in such a way that you should not be able to clone and produce many copies of this software state. And formally speaking, the way we define security is in terms of a tripartite adversary. There is Alice, Bob, and Charlie. Alice receives a software state that is obtained by applying this copy protection function, and then it produces a bipartite state. So what we want is that both these parts, which could be entangled with each other, should not be used to replicate the original functionality. So in other words, if I compute Bob and Charlie on inputs XP and XC sampled from some distribution, then the probability that they win, which is when the outputs are match the outputs of the function, the probability that they win should be low. So this notion was first introduced by Aronson in 2009, and since then it has been an important problem in quantum cryptography. It was open for a long time how to achieve copy protection, and very recently we showed that for some contrived unlearnable functionalities, copy protection is actually impossible to achieve. And for some interesting cryptographic functionalities, we do have some positive results. So for instance, random functions, decryption functionalities, signing functionalities, and so on. But the problem with all these feasibility results is that they assume I/O. And while there has been remarkable progress in constructing I/O, we still don't know how to achieve post-quantum secure I/O from concrete cryptographic assumptions. This is still a challenging open problem. So it will be interesting to see if we can actually minimize the assumptions in these constructions. But it turns out that even this is a long-standing open problem in quantum crypto. So if, for instance, if you're able to remove I/O from some of these applications, then you get public key quantum money without I/O, which is a very important problem in quantum crypto. So what we are going to do is, while we are hoping to build I/O from concrete assumptions, we should also try to look for weaker security notions of copy protection that are still meaningful and that we can achieve it from better cryptographic assumptions. So this is our research agenda to initiate this area called as revocable cryptography, which is weaker than copy protection, but it turns out that we can build many of these things from learning with errors. And we study many primitives such as public key encryption, fully homomorphic encryption, random functions, and so on. Okay, so let me first briefly describe what revocable public key encryption is. This is a regular public key encryption scheme, except that I also associate decryption key with a quantum state. So there is an additional security guarantee that we need from revocable public key encryption, which is the following. So there's a challenger who gives the decryption state to the adversary. So the adversary can use this decryption key state to decrypt how many of our ciphertext it wants. And after some time passes, the challenger will ask the adversary to return back the state. Note that this is sort of an inherently quantum phenomenon. So for instance, if this was classical, it doesn't make sense for the challenger to ask the adversary to return back the state. Whereas, due to the no cloning principle here, it makes sense for the challenger to ask the adversary to return back the state. So informally, what we want is that once the adversary returns back the correct state, it loses the ability to decrypt ciphertext. Specifically, what we want to say is that it should not be possible for the adversary to simultaneously return back the correct state and break semantic security. Or rather, they should only hold with negligible probability. And if you're familiar with software leasing, this is finite term key leasing, except that we also allow the adversary to be malicious in the last phase. Okay, so let me give the formal definition very briefly. So again, this can be thought of in terms of similar to the copy protection security guarantee. The challenger gives the decryption state to the adversary, Alice. The Alice returns back the state. Once the adversary returns back the state, I'm going to apply this measurement, this projective measurement that just checks if the state returned back is the correct state or not. And then simultaneously, I also ask the adversary Charlie to break semantic security. So I give him either encryption of 0 or encryption of 1, and I want Charlie to tell me which ciphertext I gave him. Okay, so security guarantee just says that it should not be possible to simultaneously revoke and break semantic security. Revocable through random functions is defined similarly. I have something called as an evaluation key, which is a quantum state using which I can still produce the outputs of this random function. The only difference is that instead of Charlie breaking semantic security in public encryption here, he is distinguishing whether he gets the output of a PRF or something uniformly at random. So Y0 here corresponds to the output of the PRF on X. Y1 corresponds to something picked uniformly at random. So we have a similar guarantee here as well. Okay, so what do we show? We show that assuming some conjecture that I'm not going to define, you can look at our ePrint version. So we show that dual rega of public encryption is actually key revocable. And assuming the same conjecture, we also show that the dual GSW fully homomorphic encryption is key revocable. And we also come up with a new construction of pseudo-random functions, and we show key revocability of it, again, assuming the same conjecture. So I should mention a very interesting and exciting concrete work by Agrawal et al., who showed that there exists some public key encryption that is key revocable, assuming any post-quantum secure public key encryption. So the difference is that we wanted to study like key revocability of dual rega encryption, whereas they come up with a new encryption that is tailored to be key revocable. Okay, but this work doesn't study the other two results. For instance, the fully homomorphic encryption was not even studied in the copy protection setting. So this is something new. And also for pseudo-random functions, copy protection of pseudo-random functions was studied, but it was based on IO, whereas we can show how to construct the same without using IO. So we also study a stronger notion of key revocability called as classical revocation. So here, instead of returning back the state, I actually return back something classical. So I perform some deletion operation on the state, and I get something classical, and I return back the state, I return back the classical string. And the requirement is that the classical verification algorithm and the semantic security should not simultaneously hold. Okay, so we get the same results based on a slight variant of the previous conjecture, but the advantage is that all these different results have classical revocation. Okay, so let's look at some high-level ideas about how to achieve a revocable public key encryption. So again, we start with dual rega encryption that we are all familiar with. So the public key is an n cross m matrix. Here it is denoted by a bar. You should think of m to be at least n log q. And then I also going to pick an m-dimensional vector y. And in the dual rega encryption, the decryption key is some short vector x says that a times x equals, or a bar x equals y. But here we need a quantum decryption key, and the quantum decryption key is very simple. What I'm going to do is I'm going to consider a superposition over all the short solutions that map A to Y. Okay, so specifically, we consider a superposition where the weights correspond to the truncated Gaussian with mean 0 and sigma, which is standard deviation, is going to be something like poly in M. Okay, and the encryption algorithm is the same as before. So in order to encrypt, I'm going to compute, S times A plus some noise vector. I'm going to denote this using this approximate symbol. And then I'm going to also compute S times Y. I'm going to shift S times Y with some message times Q02. So you can see that using a classical decryption key, you can decrypt and recover mu. Using the quantum decryption key, also you can recover mu. The way you do this is just to run the classical decryption algorithm coherently on the quantum state. Okay, so this is the dual rega encryption. So how do we show that this is secure? So I want to give some ideas. I will not be able to fully sketch the proof. So I want to show that you should not be able to simultaneously return the state and break semantic security, right? Okay, so now suppose let's say he returns the state. Then we want to argue that he cannot break semantic security anymore. The other extreme case is maybe he keeps the state, in which case we want to say that the revocation doesn't succeed. But of course, he can do something more complicated. He can do some convex combination of these two strategies, and we want to even rule this out. So to give some intuition, what I'm going to do is I'm going to forget that he has to return back the state. Okay, so let me just focus on semantic security for now. How do you argue that semantic security holds? Again, we want to show that encryption of 0 is indistinguishable from encryption of 1. And if you open up the ciphertext, you have S times A, S times Y versus S times A, S times Y plus Q02. You want to show that these two are indistinguishable. So what we are going to do is we are going to first apply the Gaussian collapsing lemma, which says that either I give you the state or I give you something that is obtained by measuring the state in the computational basis. And you should not be able to distinguish which are the two cases you're in. And we're going to first apply this lemma. Once we apply this lemma, we collapse the state psi y to be some classical string. And once we do that, then things become more classical. That lets us use existing techniques that were explored in the leakage resilience of learning with errors to argue that the indistinguishability of CT0 and CT1 boils down to something like a Goldrake-Levin problem over F cube. So it boils down to distinguishing the inner product of U and X0 versus U and X0 shifted by this keyword. So once we do that, we apply what is called as quantum Goldrake-Levin or large finite fields to extract X0. Right? So X0 is some short solution that maps A2. Okay, so let me quickly wrap this up. So the problem is now we have to argue that this simultaneously holds. So we can extract simultaneously well when the revocation is succeeding. And we don't know how to do this just assuming learning with errors. That's why we need this new conjecture to let us get to this point. Okay. So once we do the conjecture, then what we're going to do is instead of measuring the state using this projective measurement M, what we're going to do is we're going to measure the state in a computational basis. It turns out that if earlier the adversary was succeeding with inverse polynomial probability, it still succeeds with inverse polynomial probability even if you measure in the computational basis. And once you do this, you're almost done because you have two short solutions, X0 and X1. They both are short, they're different, and you can use this to break SIs. So this is how we prove semantic security. And since I don't have time, I'm not going to be talking about FHE and sort of functions. I just want to mention that proving revocability of FHE is easy because we are working with dual Regev encryption. We just have to look at the dual version of GSW, and you can easily argue. For pseudorandom functions, we had to come up with a new tailored construction and prove it to be key revocable. But both FHE and pseudorandom functions, we argue security by reducing it to the security of dual Regev public key encryption. Okay, so just to conclude, we come up with weaker notions of public protection that we can base it on assumptions that don't involve IO. So since our work, there has been a follow-up work that comes up with another construction of public key encryption, FHE with classical communication, assuming just LW, they don't need the conjecture. But that still doesn't solve the problem that we set out to solve, which is to prove that dual Regev encryption is key revocable. That's still open. It would also be interesting to look at revocation for other functionalities. And an even harder problem is to come up with call protection for interesting functionalities from just learning with errors. This I conclude.
Any questions for the speakers? Let's thank all the speakers of this session. And we can head over to the coffee break outside.